Hello guys, welcome back to my channel. This is another video of the Megaclock project, and I really recommend you, if you're new to the project, watch the first video because I will give you an overall introduction to the project. This video is now about the electronics and the drive. So for the drive, I bought this board from AliExpress. It is actually made for 3D printers and stuff, so it's Arduino Nano, and there are then 3 sockets for step motor drivers. So since for the clock I need only one driver, I will remove this socket here at all, because there comes the cable from the motor out in my design, and then I can plug it in here. So the plug would be in the way of this socket. So I remove that one, and the other one I use to install this DCF77. It's like a radio controlled clock module. In Europe there is this radio station in Frankfurt, and it sends out every minute the current time, encoded with a, I think, around 70 kilohertz signal. And this is the antenna for it, a ferrite rod of ferrite with copper wire around, so for inductivity. And this is the receiver, and then you have a little IC, and you get the signal demodulated out of one pin. So it's just one pin interface for the Arduino, and it's just making high and low and have some modulation on it, and it's repeated really every minute, so you get a really precise time information every minute. So that's why I don't have to rely on the precision of the Arduino clock itself, so I rely on the precision of the radio signal clock. The interface is quite easy. It's just ground, and then you have a supply voltage, and then you have the signal. So this is what I then connect to this second motor driver interface instead. So this was the first step. So for the clock project, we also need on the board 2 inputs, which are for the Hall sensors for the position of the pointers. So for that we solder on here on the leftover driver part, where we already removed the remaining sockets. We will solder on then here on the input pins 7 and 4 a little circuit for the switches. We just use the 5 volts and 10k resistors and the 100 nano capacitor for debouncing.
before we come to the software, here a quick summary of the hardware. Sure, we have our Arduino Nano on the carrier board, which is from the CNC shield. Then we have our read contacts to read back the position of the pointers. We have two digital inputs. The stepper driver was the A4988 to drive the NEMA 70 motor. And we have a DCF77 receiver. So how does it look on software side? For the DCF77 receiver, I use the TS-LNBAS library. For the stepper motor driver, I use the Axle stepper, and the read codecs for sure are only digital read inputs. On the Arduino Nano itself, then also there is the time lib, which has its internal timekeeping. How to show the correct time on the pointers. At first I thought this is quite easy, but then the devil is in the detail, we say sometimes. So let's assume we have here the real past time, in which in this diagram we say it's a 45-degree line. At some point in time we get a correct timestamp of the DCF timer module. Let's say here it's randomly, but we get the correct real time. With that timestamp, we can set the internal time. So this is another time we have. This timer library does not run in exactly parallel to the real past time because it depends on the internal clock reference of the Arduino. So there might be some deviation. It's here for sure exaggerated. It won't be that much, but for sure we have some deviation. So, and just whenever I have the DCF lib timestamp, I can set again the internal clock, and that's fine. As long as we assume we would have every few minutes a valid timestamp of the DCF lib, so this deviation will be very low. But in the other case, if we assume we don't get that many timestamps from the DCF receiver, this deviation can sum up. So over weeks and months, the clock would run away internally. And yet we have another time in the game. That's the time we show with our pointers. In this time goes exactly parallel to the timer lib time, because these two are driven by the same Arduino clock source. So they have the same deviation. And we can set the pointers in the beginning for sure when we initialize the clock. But then over time, for instance, we also have summer winter time changes on. From once in a while we have to set the pointers. The best way to do it is when we get the reset position of the pointers. So in my case I chose 4 o'clock in the morning, so there's almost nobody looking on the clock. I stop the clock and sync it. So let's assume we get at some point here the reset position, and then we can set it to the internal clock, because the DCF time we only get spots of it, only a glimpse once in a while, so we cannot set it to there. But that also means I will always set it to the deviation from the internal time to the real time. So to avoid that, I figured out that I can calculate the deviation. And this is exact when I get a DCF lib timestamp. Then I can take this deviation here, shown by the parentheses, and set it into relation with the real past time, which is here between the two timestamps. With that, I can calculate a correction factor, which can then, let's say, move the slope to the real past time. Having now this correction factor, at some point when I am at the reset position, I know the deviation, and I must not set it to the internal source, but I can recalculate with the correction factor the real past time, and then I can set it exactly on the black line, and this is where I want it to have. So how does it look in the software. Here on the right, you have our main loop. For sure, there's initialization and then the infinite loop. In the infinite loop, we move the motor according to the steps there are to move. Then we read back the read contacts to know if we are in the reset position with our pointers. And this is a little workaround, I tell you. I chose, for instance, 4 in the morning. I paused the motor to give the DCF receiver an opportunity to get a time signal because I found out that the DCF receiver is just disturbed by the motor signals, and so I have to work it out somehow to give it a chance to get a signal. So that's what I do here. But at the same point where I pause the motor, this is also my reset position, and at 4 in the morning then I synchronize the pointers to the internal clock, which is given by the timer.h. But I don't synchronize it, as I said before, to just the internal clock source. I correct it by this correction factor I calculate and then I set it. Then I have the real pause time on my pointers. Then I have here this timer interrupt routine. I use here timer 1 because timer 1 is not occupied by the timer.h and not by the Arduino itself. And this gives me like the tic-tac, yeah? So whenever the capture compare register is reached, I count here a global variable up. So I count up one step every time this timer reaches its maximum. And then when the main loop comes to move motor, it moves the steps which were added up by the timer routine. And this is which gives me almost every second like my tick. I agree that it would have been nicer for the trimming to tune the internal clock of the Arduino, but I really did not come up with any solution or any possibility for that. So I worked out this method I showed you before by calculating a correction factor. So that's about it, how all the software works. You can download the code at my webpage. Please have a look. Let me know if you have any better idea in the comments, and thanks for watching.